Alright, this is the second video on section 6.1 covering power series as functions, and we're going to go through a variety of different examples of finding the interval and radius of convergence. So our first example, we need to figure out what this limit is before we can tackle the problem, and we're going to look at the limit as n approaches infinity of n over n plus 1, and then that's quantity to the 2n power. If we try to see what kind of form this is, the n over n plus 1 is going to go to 1, and the 2n is going to go to infinity. So we have the form 1 to the infinity, and so one of our strategies is using the L'Hopital's rule, but we have to be of the form 0 over 0 or some sort of infinity over infinity. So this is going to require the logarithmic technique. So first thing we're going to do is we're going to assume that this limit exists. We're going to call it y, and then we're going to take the natural log of both sides. The natural log of the limit as n goes to infinity of n over n plus 1 raised to the 2n power is equal to the natural log of y. Okay, using the fact that the natural log is continuous, we're going to slide the natural log past the limit. So we're going to have the limit as n goes to infinity, and then we're going to use the property of logarithm, the power rule, to bring down the 2n as a factor. So this is going to be a limit as n goes to infinity of 2n, natural log of n over n plus 1, and that's going to be equal to the natural log of y. Now we'll reassess what the form is. So 2n is going to go to infinity as n goes to infinity, and the natural log of n over n plus 1 is going to go to the natural log of 1 as n goes to infinity. Natural log of 1 is 0. So that's not quite a form for the L'Hopital's rule yet, but we can employ a trick we've used previously involving infinity times 0. Okay. So we're going to rewrite this as the limit as n goes to infinity of 2 times the natural log of n over n plus 1, and then that all over 1 over n. And that's going to be equal to the natural log of y. Now let's take a look at the form. So you're going to have the natural log of 1, which is 0, and then 1 over n as n goes to infinity is going to be 0. So now we have finally the form infinity over infinity. We have the form 0 over 0, so now we can apply L'Hopital's rule. So this is going to be the limit as n goes to infinity of 2. So we're going to take the derivative of the natural log of n over n plus 1, which is going to be 1 over n plus 1. And then we got to take the derivative of n over n plus 1. So we're going to use the quotient rule. So the low function n plus 1, derivative of the top, which is n, will simply be 1, minus the top function of n times the derivative of the bottom function of n plus 1, which will just simply be 1, all over n plus 1 squared. And now take the derivative of the bottom, 1 over n will become negative 1 over n squared. Okay, let's fix our syntax here real quick. Alright, now let's go ahead and simplify this down. So this is equal to the natural log of y still. So this is going to be the limit as n goes to infinity of 2 times n plus 1 over n, so we're going to take the reciprocal of the 1 over n plus 1. Then we'll simplify the second fraction, the n plus 1 times 1, minus n times 1, all over n plus 1 squared. That's just going to be 1 over n plus 1 squared. And then we're dividing by negative 1 over n squared, so take the reciprocal of that and change it to multiplication, so it'll be negative n squared over 1, and that's going to be equal to the natural log of y. And we'll simplify this down a little bit. So this is going to be the limit as n goes to infinity of 2 times, let's see, it's going to give us a negative n in the numerator and an n plus 1 in the denominator. That's going to be equal to the natural log of y. So now we can find what this limit is. So the limit as n goes to infinity of 2 times negative n over n plus 1. The horizontal asymptote of that is just going to be negative 2. So as n goes to infinity, the natural log of y is going to be going to negative 2. So y is approaching e to the negative 2 as n goes to infinity. So we're going to use this result in finding the interval and radius of convergence of a certain power series. So we're going to go ahead and look at this on the next slide. So for our reference, the limit as n goes to infinity of n over n plus 1 to the 2n is equal to e to the negative 2. So we're going to use that result here. And number 7 here, we're going to find the interval and radius of convergence of the sum n equals 0 to infinity of 2n factorial x to the n divided by n to the 2n. So typically, the ratio test is going to be our go-to method. Sometimes maybe the root test. The ratio test handles n factorials quite nicely, so we want to use the ratio test here. So we're going to look at the limit as n goes to infinity of 2 times n plus 1, and then that's going to be a factorial, x to the n plus 1, divided by n plus 1 raised to the 2 times n plus 1, divided by 2n factorial x to the n all over n to n. And so we're just applying the ratio test here. So we're going to rewrite this now. So this is going to be limit as n goes to infinity, and it's going to be 2n plus 2 factorial. So that's 2n plus 2, 2n plus 1, and then 2n factorial. X to the n plus 1 will be x to the n times x all over n plus 1, and we're going to go ahead and rewrite that as n plus 1 to the 2n and then n plus 1 squared times, and then we're going to take the reciprocal of the dividing fraction, so that'll be n to the 2n divided by 2n factorial x to the n, and this will be the limit as n goes to infinity, and then we're going to play the absorbing game. So 2n factorial x to the n's absorb, and then we're going to go ahead and group the 2n plus 2 and the 2n plus 1 with the n plus 1 squared, okay? So that's just going to be a trinomial over a trinomial, and they're both going to be degree 2, so it's going to have a horizontal asymptote of 4. And we're going to group the n plus 1 to the 2n and the n to the 2n. So we're going to use properties of exponents to write that as n over n plus 1 to the 2n, which was the thing that we spent the last slide on finding what the limit of that thing was. And then we just have one more x left over. Okay, so 2n plus 2 times 2n plus 1 all over n plus 1 squared. That is going to give you 4n squared plus 6n plus 1 over n squared plus 2n plus 1. And so the limit of that, as n goes to infinity, the horizontal asymptote of that is just going to be 4. So we have that. And then the n over n plus 1, all that raised to the 2n, we found that that was e to the negative 2. And then we just have the absolute value of x. We're applying the ratio test, so we want to know when this converges, and that's when the common ratio is less than 1. So that's going to say that the absolute value of x must be less than e squared over 4, which would be telling us that the interval of convergence is negative e squared over 4 to positive e squared over 4. And our radius of convergence is e squared over 4. And it might be a little bit difficult to find the convergence at the endpoints here, so we're not going to find whether it converges or diverges at the endpoints here. All right, let's go ahead and look at a couple more examples here. So example number 8. We're going to find the interval and radius of convergence of the sum n equals 1 to infinity of 8x to the n over n. So we're going to look at using the ratio test again. So the limit as n goes to infinity of 8x to the n plus 1 all over n plus 1 divided by 8x to the n all over n. That's going to be equal to the limit as n goes to infinity of 8x to the n times 8x all over n plus 1, and then flip the divisor fraction, so that's going to be n over 8x to the n. Okay, the 8x to the n's will absorb, so we have the limit as n goes to infinity of n over n plus 1, absolute value of 8x, the limit as n goes to infinity of n over n plus 1 is going to be 1. So this is going to be 1 times the 8, and then we'll put the absolute value just on the x. And that's going to be less than 1. Okay, then we're going to divide both sides by 8. So this says the absolute value of x is less than 1/8. So it says negative 1/8 is less than x, which is less than 1/8. In this series here, we actually can pretty easily determine whether it converges at an endpoint. So if x is equal to negative 1/8, you're going to have 8 times negative 1/8 to the n. That's going to give you negative 1 to the n. Okay, so our series becomes the sum n equals 1 to infinity of negative 1 to the n over n. And previously in the alternating series video, we would have shown that this is a convergent alternating series. So this converges by the alternating series test. Okay. So for our interval of convergence, we do know that it converges at the left endpoint of negative 1/8. Now let's look and see what happens at the right endpoint of 1/8. If we plug in 1/8, it's going to be 8 times 1/8 to the n, which is going to be 1 to the n, which is simply 1. Oops. So this is going to be x equals 1/8, so that's going to give us the sum n equals 1 to infinity of 1 over n. And we know this is a divergent p series. This is the harmonic series where your p is equal to 1, and that's less than or equal to 1. So we have divergence at the right endpoint, and our radius convergence is 1/8. Okay, I think we have 3 more examples, so let's go check out the next one. So we're doing the same thing. We're finding the interval and radius of convergence. So we're going to look at the sum n equals 1 to infinity of 9x to the n over n to the 8th. So we're going to look at using the ratio test again. So the limit as n goes to infinity of 9x to the n plus 1 over n plus 1 to the 8th divided by 9x to the n all over n to the 8th. So it's going to be the limit as n goes to infinity of 9x to the n plus 1, which we can rewrite as 9x to the n times 9x divided by n plus 1 to the 8th. And then we're going to flip over the dividing fraction, which becomes n to the 8th over 9x to the n. Notice that the 9x to the n's are going to absorb, and so we can write this as the limit as n goes to infinity of the absolute value of, and so what we're going to do is the n to the 8th over n plus 1 to the 8th is rewrite that as n over n plus 1 quantity to the 8th, and then times 9x in absolute value. And we take the limit of that. The limit as n goes to infinity of n over n plus 1 is going to go to 1. Raise the 8th power will just be 1. And so this limit is going to be 9 times the absolute value of x. And that's going to be less than 1 when the absolute value of x is less than 1/9. So we have x needs to be between negative 1/9 and positive 1/9. So let's go ahead and check those endpoints. So if we have 9 times negative 1/9 to the n, that's going to be negative 1 to the n. Okay, so our interval convergence is going to be negative 1/9 to positive 1/9, and we just need to check the endpoints. So when we plugged in x equals negative 1/9, our series our power series became sum n equals 1 to infinity of negative 1 to the n over n to the 8th. If we apply the alternating series test, this will certainly converge. So this is convergent alternating series. Okay. Now, when we look at x is equal to 1/9, we have x times 1/9 to the n, so that's just going to be 1 to the n, which is simply 1. Okay, so x equals 1/9. power series becomes the sum n equals 1 to infinity of 1 over n to the 8th, and that's just a convergent P series. So it's a convergent P series. P is equal to 8, and that's greater than 1. Okay, and so we have convergence at both the endpoints. So it's certainly possible to have convergence at both endpoints, at one endpoint, or none of the endpoints. All right, 2 more to go. Let's look at the sum n equals 1 to infinity of 11 to the n, x to the n, n plus 1 over n plus 10, and we're going to apply the ratio test. So limit as n goes to infinity of the absolute value of 11 to the n plus 1, x to the n plus 1, n plus 1 over n plus 1 plus 10, divided by 11 to the n, x to the 10, n plus 1 over n plus 10. That's going to be the limit as n goes to infinity of 11 to the n times 11 times x to the n times x times n plus 2 over n plus 11, and then we're going to flip over the dividing fraction, so n plus 10 over 11 to the n, x to the n, and n plus 1. Okay, so it's going to be the limit as n goes to infinity. Let's see, the 11 to the n and the x to the n's will absorb. And let's see what we got going on. So we got n plus 2 times n plus 10 times 11 x all over n plus 11 and n plus 1. So that's going to give you n squared plus 12n plus 20 over n squared plus 12n plus 11. So the quotient of the leading coefficients is going to be 1 over 1. We have a tie in degrees, so that part is just going to go to 1. So our limit is going to be 11 absolute value of x, and that needs to be less than 1. So the absolute value of x must be less than 1 over 11. So it's going to say negative 1 over 11 is less than x, which is less than 1 over 11. Okay, now we essentially have 11x to the n, it's just separated. So we'll look at 11 times negative 1 over 11 to the n, and that's going to give us negative 1 to the n. Or 11 times 1 over 11 is our other endpoint to the n, will just give us 1 to the n, which is 1. Okay, now regardless of whether it is minus 1 to the n or just 1, when we look at the limit as n goes to infinity of the n plus 1 over n plus 10, that is not going to be equal to 0. And that is the nth term test for divergence. So the only difference here is if it's the negative 1 over 11, we have this negative 1 to the n, and so that just alternate between minus 1 and 1, and so this certainly doesn't converge. And so we are not going to converge at either one of the end points here, and that is by the nth term test for convergence. Excuse me, nth term test for divergence. Okay, all right. So x equals negative 1 over 11. We have the sum n equals 1 to infinity of negative 1 to the n plus 1 over n plus 10. And if x is equal to 1 over 11, we have the sum n equals 1 to infinity of n plus 1 over n plus 10. Both of these are going to diverge by the nth term test. So that means we do not have convergence at either one of the endpoints. So our interval of convergence is going to be negative 1 over 11 to 1 over 11, not including the endpoints, and the radius is going to be 1 over 11. Okay. Alrighty, we got one more example for this video. We're going to look at the sum n equals 1 to infinity of n squared, x plus 9 to the n, over 9 to the n to the 8/3. Again, we're going to apply the ratio test, so this is going to be n plus 1 squared, x plus 9 to the n plus 1, divided by 9 to the n plus 1, and n plus 1 to the 8/3, divided by n squared, x plus 9 to the n, divided by 9 to the n to the 8/3. Okay, so this is going to be the limit as n goes to infinity of n plus 1 squared, x plus 9 to the n, x plus 9 to the first, divided by 9, n, 9 to the n times 9, n plus 1 to the 8 thirds. And then flip the dividing fraction, 9 to the n to the 8 thirds, all over n squared, x plus 9 to the n. X plus 9 to the n's are going to absorb, and the 9 to the n's are going to absorb, so this is equal to the limit as n goes to infinity. And we can group the n plus 1 squared with the n, and that's going to be n plus 1 over n quantity squared, so that's grouping the n plus 1 squared with the n squared. Okay. And then we're going to group the n to the 8 thirds with the n plus 1 to the 8 thirds, and gives us n over n plus 1 to the 8 thirds. And then what we got left is the x plus 9 over 9 in absolute value. Now both the n plus 1 and the n over n plus 1, those limits are going to both be 1. 1 to the second power and 1 to the 8 thirds, those are going to both be 1. So this limit is going to be the absolute value of x plus 9 over 9. We want convergence, so less than 1. So go ahead and multiply by 9, so the absolute value of x plus 9 must be less than 9. So negative 9 is less than x plus 9, which is less than positive 9. So negative 18 is less than x, which is less than 0. Okay, so this particular series, the x plus 9 to the n over 9 to the n, we can rewrite that as x plus 9 over 9 to the n. When x is equal to negative 18, you're going to have negative 18 plus 9 over 9 to the n, and that's going to give you negative 9 over 9 to the n, or negative 1 to the n. Okay, so it's going to make this an alternating series. If the x is equal to 0, the x is equal to 0, x is 0, then we have 1 to the n, which is simply 1. Okay, and so that'll give us a p series. So we're going to go ahead and erase this. Okay. Alright, so when x is equal to negative 18, the sum becomes the sum n equals 1 to infinity of negative 1 to the n squared over n to the 8 thirds. And if we apply the alternating series test, this is going to be a convergent alternating series. And so we can include the right endpoint. We can include the left endpoint. Now if we look at x is equal to 0, the power series becomes the sum n equals 1 to infinity of n squared over n to the 8 thirds. That is a p series. It's going to be the sum n equals 1 to infinity of 1 over n to the 2 thirds. And that is going to be a divergent p series, where the p is equal to 2 thirds, and that's less than or equal to 1. So that means we cannot include the right endpoint. Our radius of convergence is going to be 9 here. Okay, so I got one more video for you. It's going to probably be a little bit shorter than this video. So we'll see you next time.